Hello, and welcome to our Analytical Foodies bite-sized webinar series. This series will provide hints and tips to help you be successful with your multi-residue analyses. My name is Emer McCall, and I'm a Principal Market Development Manager here at Waters Corporation. The topic of this episode will look at a number of methods to reduce or eliminate matrix effects during method development. In previous episodes, we've touched on the benefits multi-residue methods can offer labs in terms of productivity. Of course, in running these methods by mass spectrometry, matrix effects are a common occurrence. In this episode, we'll discuss three approaches to reduce or eliminate matrix effects, namely by sample cleanup, dilution, or chromatographic separation. Let's begin with the approaches most commonly employed in routine analyses. In another episode in this series, we looked at how to calculate matrix effects. Taking some of the data and calculations discussed in that bite-sized webinar, we can see the matrix effects determined for fipronil in egg. In this example, we've spiked a crude Ketcher's egg extract to the required reporting limit of fipronil and the equivalent concentration in a solvent-based standard, similar to matrix-based solvent diluent. Using the matrix factor tool within MassLynx, we can see that fipronil is suppressed by the egg matrix, which is also evident by looking at the overlaid fipronil peaks acquired at the same concentration. So what can we do to correct these effects? Sample cleanup is a standard solution in mass spectrometry methods. With a selection of protocols to choose from, some common approaches include liquid-liquid extraction, solid phase extraction, or dispersive solid phase extraction. The main benefit of sample cleanup is the cleaner extracts injected onto our system. Of course, this reduces matrix effects, but it can also have a positive impact on the lifetime of the analytical column, the injector, and reduce the frequency of routine maintenance. In this example of fipronil in eggs, we've applied a solid phase extraction cleanup by simple pass-through using Oasis Prime HLB. It should be noted that we've determined analyte recovery separately to the matrix effect study we're discussing here. To understand the impact on effects specifically, we've run fipronil again at the required reporting limit. We can see that matrix effects between the solvent-based and cleaned-up matrix-based standard are negligible. To see this in the overlaid chromatography, we've offset the y-axis so that we see two peaks which are equivalent in response. By removing these effects, we've reduced the variability between samples, thus increasing the method's reliability. This can be seen in the percentage CVs reported in the matrix factor tool for the crude Ketcher's and cleaned up Ketcher's extract of egg, where the precision is improved by more than a quarter for the cleaned up extract. These same results are reported within the statistics tool in TargetLynx, where the performance for the multiple analytes can be viewed in a single screen. Similar elimination of effects are observed for the slope of the line approach, used to determine matrix effects, as we see here in this overlay across the working concentration range. Of course, it's not just the method's reliability and system uptime that's improved by removing these effects. But as we can see with this calibration overlay, we may consider quantitation against a solvent-based curve, which may save additional time and cost of consumables during sample preparation. This method for reducing matrix effects offers many benefits and should always be prepared. However, in multi-residue methods, finding an appropriate cleanup to address a broad range of analyte to commodity scope may not always be achievable without impacting analyte loss during cleanup. Another option, which has seen a large increase in recent years, is the dilution of the final extract prior to injection. It's a simple yet powerful solution that, based on the sensitivity of the detector, may be worth checking during method development. So what does diluting out the matrix look like in practice? Again, taking Ketcher's extracts, this time of soybean, we've run a number of injections and acquired all data in full scan on our tandem quadrupole mass spectrometer. Looking at the overlaid profiles, we see the highest background from the matrix in the crude extract. As we dilute the extract by a factor of 5, shown here in pink, and a factor of 10, shown in yellow, we see the response of the background trace decrease. Not surprising, of course, we've simply diluted down the matrix. But what impact does this have on the analytes of interest and the matrix effects we're trying to overcome? Of course, given the intensity of the background across all extracts, it is still difficult to see our targeted analytes acquired in time-windowed MRM mode. But if we zoom in to 3.8 minutes in this example, we can see the response for carbofuran 3-hydroxy in the neat and the diluted extracts. This may strike as counterintuitive, but as we can see on screen, by diluting our final extract by a factor of 10, we can see the response of our analyte double. This is because the dilution has reduced the number of components entering the ionization source simultaneously with our analyte, and so less competition for efficient ionization. This 10 times dilution factor yielded great results across commodity groups for over 500 pesticides. However, significant effects were still observed for a number of analytes in the scope. This included carbofuran 3-hydroxy, which showed approximately 30% suppression. While the dilution step offers great benefits in reducing matrix effects, it may need to be considered in combination with another approach to ensure effects are overcome sufficiently. One more approach that can aid in reducing matrix effects is optimizing the chromatographic separation of your analytes of interest from the co-eluting matrix interferences. If we can reduce the components arriving into the source simultaneously, then we can minimize the competition for ionization and improve droplet formation and desolvation. As we've discussed in another episode of this bite-sized webinar series, there are many factors that influence chromatographic performance, such as the column stationary phase, the particle size, and mobile phase compositions. These factors can be investigated to help reduce matrix effects, depending on your analytical method. In this example, we're keeping it simple and looking only at the ramp applied to the changing LC gradient. Taking anionic polar pesticides as an example, AMPA, which is a metabolite of glyphosate, is renowned for experiencing 80 to 100% ion suppression in the acidified methanol-based extraction solution used in the QUIPI method. This is due to the highly polar nature and similar physicochemical characteristics with many naturally occurring components in food, such as organic acid. This, of course, limits the sample cleanup options available without impacting analyte loss. Having previously optimized the column selection and gradient to ensure good retention of all anionic polar pesticides, we can experiment with the gradient profile to reduce matrix effects without needing to worry about losing significant retention of the first eluting compound. In this example, we're looking at AMPA, spiked into a QUIPI extracted flour sample. The red trace on screen shows the high matrix background of wheat flour, acquired from full-scan data acquisition of ions between 50 and 500 Dalton, eluting in the first 3 minutes of the LC gradient. By overlaying the simultaneously acquired time-windowed MRM for AMPA, it shows the impact matrix interference is having on AMPA's peak shape and reliable detection. Quantifying this, we calculate that AMPA is being suppressed by nearly 90%. So instead of applying a steep change to the gradient within the first 2 minutes, what would happen if we alter this gradient ramp? Well, as you can see, we can improve AMPA's peak shape and response. We can achieve increased retention and reduce ion suppression by more than 30%. This was simply achieved by setting a more shallow gradient curve in the LC method, which allows AMPA increased ionization efficiency in the MS source as it is competing with less interferences. However, as we can see in the table, AMPA remains suppressed by more than 50%. So although the revised gradient curve provides more reliable performance, significant matrix effects still remain, requiring additional approaches to bring the matrix effects below 20%. So to summarize the approaches to reduce matrix effects we've just discussed, some of the main points are outlined in the table. For many multi-residue methods, one single option may not be sufficient based on the analyte commodity scope. Perhaps a combination of approaches may be required to either reduce effects as discussed here, and or to compensate for these effects, which are discussed in another episode of this series. Finding the right solution to overcome matrix effects is often method or lab specific. Hopefully this short overview provides some guidance when selecting the appropriate method to correct matrix effects experienced in your method. Thanks for viewing this episode. More episodes in the Analytical Foodies bite-sized webinar series are available on waters.com.